7:59 and the time quality bids are good. Somebody's lying. So you raise a flag and let everybody know. So it's a lie detector and takes care of the problem. So here's another way for time integrity. One thing to do is, I think it's a pretty good idea not to stick the antenna in plain sight. So you put it up high enough where maybe nobody can notice it. And that's a first offense. If you've got two antennas, you put them in different corners so it's a little harder for a bad guy to jam them both. And by the way, I'm not being alarmist about this. I'm being practical about it. So here's a GPS clock, and the satellites are hidden. Here's a terrestrial system. The ICON network will distribute precise time within tens of nanoseconds. And if you do lose a GPS, everybody on that network still thinks it's the same time to the nanoseconds, and that's good. So we talked about the IRID authentication, and then the IEDs, the relays themselves, do a quality check. So it's real easy to test clocks accurately. So here's one way of doing it. We use a satellite simulator which puts out a radio frequency signal as well as a reference pulse, 100 pulses per second. And then we can stick that through the RF into the clocks to be tested and watch them. So if you don't have this, which you probably don't, you can still check clock versus clock and they better agree. So here's what it looks like when you hook your scope up to it. And what we did here is we triggered the scope with that reference. So this is top dead center. And here's a 2488 with running on its temperature compensated crystal oscillator and GPS in an older version of a clock we make. And that's the jitter, if you will, which you can see is in the tens of nanoseconds. This is the network time from ICON, and we tested somebody else's clock and it looked like that. So I asked our guys, hey, this is pretty easy to do. Even I can do it at the tender age of 67. And I said, how do you test this PTP stuff? They said, oh, well, we got this $100,000 test box. And I said, oh, that's going to go over real well. So let's talk about something else here for a minute. And that's in networks where we got a need for speed, we have a choice. Are we going to use packet-based systems, or are we going to use time domain multiplexing systems? And we chose TDM because it's fast and it doesn't jitter. So when we're thinking about permissive tripping, when we're thinking about pilot schemes and blocking, we certainly don't want to be putting 7 or 8 milliseconds of delay into the process, because that just adds up into how much longer the fault is on the power system. Every one of those milliseconds, look at them there, every one of those at 500 kV could be another feeder. So let's talk about something else. And this is not something that was legalized in Washington or Colorado, but instead it's a high altitude electromagnetic pulse. So you hear a lot about this. There's people running around Capitol Hill. By the way, if you and I have a good idea for a business, we're going to go do it ourselves. If the idea is not so good, we'll try to attract other investors. And if the idea is a real pig, we'll go see if we get Congress to pay for it. So, anyhow, the idea is people are worried that some bad guys will set off a specific type of nuclear weapon, and it'll put out a great big electromagnetic pulse. And that big pulse will fry all the electronics and will be bombed into the Stone Age. And there's novels written about it, and unscientific people get real scared about this stuff. Now, I am worried about people setting nuclear bombs off over my head. I don't want you to get the wrong idea here. But we say, in God we trust, all others bring data. So let's put some data on this. So here's a protective relay, and it's inside essentially a waveguide made up of these copper tubes held up by Schedule 40 PVC pipe. I keep thinking if this test lab had painted those, they could have made it look a lot more expensive than it really was to build that thing. I'm glad they didn't. So anyhow, they set this up, and we can, the standards say you got to be able to do something like 5 kilovolts a meter for electric field strength. So we were fine up to 34 kV a meter. So that's a ratio of 7 to 1. In voltage, you square that, that's 50 to 1 more or less for power ratio, which would be 17 dB, better than that, okay? So then the things are in a panel in a control house. So neglecting the panel, and just suppose that the relays is floating magically inside a control house. So we took some gear into where we build the modular control houses in San Luis Potosi, Mexico, and we put an antenna outside with the receiver and inside with the source to see what happened. And we got 40 dB when through the roof. That's how the attenuation is. Very little came out there. Through the typical wall section, 30 dB. And if you took the antennas right around the cracks of the doors, if somebody's going to set the nuclear bomb off right near the door crack, well, it wasn't all that good. But this was a standard house. We didn't do anything to it to make it better. So in any case, because we have those extra 17 dB and you take these 10, well, we still got plenty of margin no matter what you assume for the control house. And that's how easy it is to deal with the problem. If you're really worried, then you can put in a better door. But I don't think it's worth the trouble. So let's shoot them. I just thought you guys would like to see some of the fun tests we get to do in addition to the regular ones. So people want to know just how ballistically safe these things are. So there's a standard, and we did UL 752 level 4. I asked the guys who did this test, one of them being my son Eddie, if we had a video of the actual test, and he said no, but he was very interested in going out and repeating the test with high-speed video cameras. So lacking that, I asked if somebody could find a video of tests, a ballistic test online to fill in that gap. Do not try this at home. Okay, so what about fire? Some people have asked us about fire, so we set them on fire. This is a steel or concrete panel with a steel frame, and the idea was 2 hours of fire to make sure it could still withstand 2,000 pounds of load on the top. And then after that, you saw the guys with the hoses. So what another part of that standard is to make sure that the water pressure from the hoses doesn't penetrate the wall. So here's a steel wall, same kind of a test. The fire burning inside it, and here we go with the fire hose, and that's what a 2-hour test looks like. It's kind of fun to do these things and share them with you. I got one last one here. Well, this is the electrostatic discharge test. And that little white thing with the metal tip on it, that's the tip of the stun gun. By the way, one shot of that is worth about 2 cups of coffee in the morning. And the way you do that test is designed to say, okay, if ESD, if you have walk across a carpet as if the floor is carpeted in the substation and touch the front of it, that electric discharge shouldn't damage any of the controls. Our theory on these tests is when you do them, you really have to approach testing with an attitude of seeing if I can make it fail. Don't you agree?
Yeah.
Try to break it. Try to break it. So we test things to the extremes. You can see in the last part of this picture, there's a couple of resistor leads that are stuck into that DB9 connector. Because we said we want some of that energy to go into those holes, and it was just jumping to the shell. And you can see how the guy with the stun gun was delightfully getting the sparking inside those holes around the push buttons. You just imagine the electrical engineer who designed that front panel interface saying, no, don't do that, but we do it, and we want to know. So the very last one is some stuff that we've done for the United States Navy, and this is a film of some of our lightweight shock machine. And the idea is that with warships that they do get in harm's way, and you want to know that the equipment can take the shock of physical shock of exploding ordnance. So this lightweight shock machine, we built it with the help of our friends at the University of Idaho. It was kind of a fun project. And it's got a couple of 400-pound hammers on it. So next stage up from this is a 2,000-pound hammer that comes up underneath an anvil. I don't have any video on that one. And the stage after that is sea trials with charges set off underwater. So I'll show you this one, and then if we have time, we're going to have some time for questions, then we can look at the one of sea trials. So here we go. There's the hammer. Have fun. Who says mechanical engineers don't have fun at work? So what, I don't know if you noticed the round ball there with Clifford on it. So Eddie put the ball on there because the photocell was that trips the hammer would drop more reliably that way. So let's see, how are we doing on time? I'm about gone, right? 10 minutes? Okay, you want to see one more video? If we're a testing conference, we ought to, let's see, what do I need to do? Close this one? And then the other one. Oops. I can tell this isn't my computer because this one's really organized. There, here we go. How am I doing, Ashley? You doing good?
The ferocious detonation blasts the ship.
Here we go.
The ferocious detonation blasts the ship, distributing most of its total force in the initial explosion.
4, 3, 2, 1, shoot!
That was not our gear that fell out, honest.